Today we're going to start a unit on gases. To understand gases, there are four quantities that we measure. One is pressure, which we're going to look at today. Then there's also volume, how much space it takes up, temperature, and just a measure of how much gas is there, how many particles are there. Everything that we know about gases can be explained pretty easily using common sense and the idea that everything is made up of little particles, molecules, or atoms. Let's get going with pressure. First of all, let's define it. Pressure is, by definition, the ratio of a force and the area over which that force is applied. So right now I'm pushing down on my tablet with my pen, and I make a little speck there because the tip of my pen isn't very large. So the force is small, the area is also small, so the pressure is pretty small. If I were to push down really hard with my pen on that same space, pressure would get bigger, but area would be the same, and so I'd have a larger pressure. Mathematically, we could say pressure is equal to F over A. So when A is bigger, pressure will go down. When F is bigger, pressure will go up. If I push down really hard but spread the area of application over a bigger surface, well, then my pressure would drop. I read one time that a 130-pound woman in high heels exerts more pressure on the earth than the Empire State Building. Not because she weighs more than the building, but because her pressure is the ratio of force over area, and high heels don't give that much area compared with the building. Now, if we wanted to think about units, thinking about the standard unit of force in the SI system, the unit is the Newton. The standard unit of area would be the square meter, a meter by a meter. So this is what we have for an SI standard unit of pressure, a Newton of force over a square meter of area. Now, a Newton of force turns out to be fairly large for gases, and a square meter turns out to be really large for most practical purposes. And so this unit of pressure is sort of impractical, and we end up having to scale it down. It's been given a name, the Pascal, after a French mathematician and scientist kind of a guy, and the abbreviation is PA, Pascal. 1 Newton per square meter. We experience pressure all the time. We don't think about it much, but there are all these air molecules that are pushing down on the surface of the Earth. You imagine the Earth here, and it's surrounded by this layer of what we call atmosphere. All the atmosphere really is a bunch of air molecules, nitrogen and oxygen primarily, and then a few other things. Now, all of these particles are held towards the Earth by gravity. Just like if you're standing on Earth, you are held down to Earth by gravity. All the little specks that are above you follow those same laws. And so there's this pull towards the center of the Earth that's experienced by every one of these air molecules all around in the atmosphere. The accumulated weight of all that pulled down air is atmospheric pressure. If we could imagine a 1 meter square on the surface of the Earth and extend that 1 meter all the way up to the top of the atmosphere, the weight of all of that air in there would amount to a pressure of 101,325 of those pascals that we talked about earlier. Seems like a big number. It actually is. It's tons in force over a square meter because the air weighs a lot. Well, a man named Torricelli came up with a way to measure and keep track of what was going on with the atmospheric pressure. It's a way to measure relative atmospheric pressure. And what it does is it uses the height of a mercury column to do this. This is his idea. He took mercury and he put it in a long, skinny tube, kind of like a test tube, except really elongated. And then he filled a bowl with mercury and he inverted the tube into mercury. So he originally starts out with this tube completely full of mercury. And then, because mercury is heavy, it starts to fall down into the bowl. And eventually it reaches a sort of a balance because what's pushing back up is the atmospheric pressure. Call this PATM for atmospheric pressure. Atmospheric pressure pushes down on the bowl. That exerts pressure all over, like on the sides of the bowl, bottom of the bowl, and actually back up the column. So this atmospheric pressure gets transmitted up to the bottom of this column, and it holds the column up. What's pushing down? Well, the weight of the column is pushing down. When the weight of the column gets small enough that it's balanced by the atmospheric pressure, it stops going down. Then what Torricelli did was he just measured how high is it from the surface of the mercury in the bowl up to the top of his column. And he watched that from day to day to see if it changed, and it turned out that it did. Most people live where the height of this column is between 730 millimeters and about 760 millimeters most of the time. It turns out there are other things that affect it, like what's the weather doing. Sometimes there's low pressure, sometimes there's high pressure in a local region, and that means that the weather is changing. Because at sea level, most of the time the height of that column is about 760 millimeters of mercury. That was defined as a new unit of pressure. 760 millimeters of mercury is the same as what we call 1 atmosphere of pressure. An abbreviation for atmosphere is ATM. So 1 atmosphere of pressure is 760 millimeters of mercury. If you were to measure this in the United States, where we use inches, you'd find out that 29.9 inches of mercury is the equivalent of 1 atmosphere. Here are some other conversions. 1 atmosphere is also, as we've seen, 101,325 pascals. Remember, that's the pressure exerted by a column of air above the Earth. That's 1 square meter. Because that's a pretty large number, we will often use kilopascals. 101.325 kilopascals is an atmosphere. The millimeter of mercury is actually a unit, and we sometimes call this a torr in honor of Evangelista Torricelli, the person who invented the barometer. Another unit of pressure that gets used sometimes is the bar. A bar is 100,000 pascals. 100,000 pascals is a bar. This is not related to the atmosphere, but you can make a conversion factor. Because a bar is a lot of pascals, we often work in millibars. Bars are used as a measure of pressure often in very low pressure situations like vacuum tubes and things like that. And so we use millibars, and 1 atmosphere is the equivalent of 1,013.25 millibars. Remember, milli means 1/1000th, so a millibar is a thousandth of a bar. And then in the United States, 1 atmosphere is also the equivalent of 14.7 pounds per square inch, or PSIs. And in the good old US of A, we use PSIs to measure the pressure of all kinds of things, like the pressure in your tires. Most often, in the United States, would be measured in PSI. So if you go to the gas station and check your tire pressure, that little device that you use will measure how many pounds are pushing on every square inch inside your tire. There are other devices that have been invented for measuring pressure. One is the open-end manometer. In an open-end manometer, you're measuring some gas in here. Let's say this is your gas inside this chamber, and there's a little valve up there that you can open up to let the gas out. An open-end manometer is a very simple device. It's just a U-shaped piece of tubing, glass tubing or something like that. Inside there is some mercury. So before there's anything pushing on it, if you just had this thing unconnected, you'd have equal pressure on both sides. Here you'd have 1 atmosphere of pressure, and here you'd also have the pressure of 1 atmosphere pushing down. And so the legs of these columns would be the same height, because they're being pushed down by the same pressure. But now let's say we hook up the gas and then open up the valve. Pretend that this gas exerts more pressure than the atmosphere. Well, in the sort of a tug-of-war between both sides of this column, this leg is going to get shorter because it gets pushed down by the pressure of the gas. That's going to force the column on this side to get higher because it's pushed down by the atmosphere, which is less than the pressure of the gas. There's a difference here in height. We can call that delta P, and that delta P represents how much bigger the gas pressure is than the atmosphere. So the pressure of the gas, we could say, is equal to the pressure of the atmosphere plus the delta P. And you could measure that in millimeters, let's say, and you'd know the pressure of the gas in millimeters of mercury if you knew the atmospheric pressure. So let's say we knew that it was 760 torrs, or 760 millimeters of mercury one day. That was the atmospheric pressure. And then we hooked up a gas, opened it up, and we found out that this delta P here, let's say that that was equal to 55 millimeters. That represents 55 torrs, millimeters of mercury. So we could add 55 millimeters, or 55 torrs, and we'd get our total pressure of that gas. And I guess that'd be 815 torrs. Let's say the pressure of the gas inside this chamber here was less than the atmospheric pressure. So we'd start out, before it got hooked up, with equal sized legs because we'd have atmospheric pressure on both sides. So here is the atmosphere. On this side would also be atmosphere. Now we hook it up to the gas and open up the valve. The pressure of the gas is low in this particular container, lower than the atmospheric pressure. So that means the atmosphere pushes down, forcing the other side to push up. And then we could measure the distance like we did before, delta P. Only now delta P means something different. If the pressure of the gas is smaller, in other words, if the size of the leg on the gas side is higher than that on the atmosphere side, which is now down to here, well then delta P represents how much less than atmospheric pressure is the pressure of the gas. So we'd have a different relationship. Pressure of the gas is equal to pressure of the atmosphere minus our delta P. So again, let's say that this was 50 millimeters. That was the height difference in the two legs. And the atmospheric pressure, let's say, was 760 torrs, or 760 millimeters of mercury. That would mean that the pressure of the gas in this situation is 760 torrs minus 50 torrs. So that would be a 710 torr gas pressure, less than the atmospheric pressure. Well, that's kind of complicated, kind of hard to use because of the fact that you have to do this arithmetic. You have to, first of all, figure out which equation works. Is the gas pressure lower or higher than the atmospheric pressure? And then you got to plug in the numbers and do the math. That's where this device comes in. These are harder to make, but they're easier to use. This is a manometer, but it doesn't have an open end. Over here it's got a closed end. So this is originally filled with mercury, and then the mercury column settles down. So up here we have no pressure, zero pressure, because this was originally filled with mercury. And now that the mercury column has fallen down to this level, it's empty. And so there's nothing there pushing on the top of the mercury column, no atmosphere, because this end is closed off. So if we want to measure the pressure of this gas that's pushing here, P gas, we just measure the difference in height. Delta P is the pressure of the gas because there's nothing pushing down on here to balance it. We're not comparing it to any pressure, we're comparing it to zero. So delta P is the pressure of gas. Harder to make, much easier to use. Nowadays we really don't use manometers that often except to calibrate more convenient devices. Like here's an example. You can make various versions. This is just kind of a schematic of how it would work. In real life they look a little different than this. But you take a container, you can make these very small. When I was working in industry, we welded these so small we had to look at them under a microscope to inspect them. This is a relatively thick can, thick-walled container, so it's inflexible. It doesn't move very much, preferably not at all, to any measurable extent. And then you seal inside there a gas at what we call a reference pressure, a pressure that you know, like 1 atmosphere, let's say, for example, or it could be something less. And then once you know that pressure is right, you weld onto it a thin, flexible diaphragm. This is thin and flexible, sort of like aluminum foil or something like that, so it can flex back and forth. The metal can stretch because it's not too rigid. So what you're looking at is a cross section. If you slice this can in half and looked at the sliced open part, this is what you'd see. So inside you have sealed up inside this can, this reference pressure, and outside you have the atmospheric pressure, whatever it happens to be. If the atmospheric pressure and the reference pressure are the same, well, this diaphragm doesn't stretch at all. And this little linkage that's attached to it shows a needle that points right straight up at the top. So let's say we had this calibrated, that maybe be 760 torr, if that was what the atmospheric pressure was. Now watch what happens when the atmospheric pressure gets small. The diaphragm stretches out because the atmospheric pressure here can't push as hard as the reference pressure. So that flexes the diaphragm out. That pushes this link over, and because this is a pivot right here, the needle pivots down to the lower end. So maybe this is 350 torr or something like that. You'd calibrate this, of course, so that it read right. On the other hand, if the atmospheric pressure was higher than the reference pressure, look what would happen. Now the diaphragm would stretch in because the reference pressure is too small to combat the atmospheric pressure, and so that gets pushed in. Let's draw the linkage over to the left, and that moves the end of the needle to the left, and so the other end of the needle goes to the right, and then we show a higher pressure, like maybe this is 800 torrs or something like that. That's how that would work. Now, in real life, these things look a lot differently, and it's not always a mechanical linkage. In fact, nowadays, it's much more likely to be some kind of an electronic strain gauge or something that's glued to the diaphragm. But that's the basic idea. The reference pressure is compared to the atmospheric pressure, and then we use some way of telling how much bigger or smaller it is. There's another way that we measure pressure. You've probably used this before. Good old-fashioned tire gauge. Here's how a tire gauge looks. If you could slice one right down the middle, you'd see inside there this little rod, and this rod is movable. Before you hook it up to the tire, it's balanced pressure because you've got atmospheric pressure on one side of the tire gauge. On the other side, you also have atmospheric pressure. Once you hook it up to the tire, however, it's not balanced anymore. On one side, you have the pressure of the tire and the atmospheric pressure, and on the other side, you have only the atmospheric pressure. So what that does is it causes the needle to move out a little bit. If the pressure in the tire is bigger, it moves out farther. If the pressure in the tire is even bigger, it moves out farther. And so what you measure with your tire pressure gauge is you measure how far did this thing stick out before it stopped moving. And that's the pressure. It's usually measured in PSI in the United States. Something I wanted to do here is give you an idea of how you can use dimensional analysis or proportion to change pressure units, because we have to do that from time to time. So let's say I gave you this pressure. Let's say I had 685 torrs, which is 685 millimeters of mercury, and I wanted to convert that into, let's say, atmospheres. I can do this two ways. One is by dimensional analysis, my favorite way, so I'm going to do it first. Starting out with 685 torrs, remember with dimensional analysis, I want to multiply by some factor that's going to change this into the unit that I want, which is atmospheres. Well, if I think back to the definitions that I had earlier, I remember that there are 760 torrs in one atmosphere. And if I put the torrs on the bottom, they cancel, and so I'll get atmospheres. I do my arithmetic, I find out that I have 0.901 atmospheres. Let's do this with a proportion, because you can do that too. We can set up the left-hand side of the proportion by saying 1 atmosphere is to 760 torrs, as, on the right-hand side, X atmospheres is to 685 torrs. So X is going to come out to have units of atmospheres, because torrs are going to drop out. And when we cross multiply and divide, 685 times 1 divided by 760, it's the same exact arithmetic, so of course you get the same answer. You try one. Let's say I gave you 150 atmospheres, and I wanted you to change this to PSIs, pounds per square inch. Give it a whirl. Well, I'm going to do this with dimensional analysis. I know that 150 atmospheres is my starting point, and I know that I want to end up with PSIs, pounds per square inch. Here's the factor that I know. I know that 1 atmosphere is the equivalent of 14.7 PSIs. By putting the atmosphere on the bottom, I cancel it, and I give myself PSIs. I need 3 significant figures. My answer comes out to 2,205, so I have to write that in scientific notation to get the sig figs right. 2.20 times 10 to the 3rd PSIs.